So, Elaine, you have been annoying me for all these years
Now you do.
with the same question, which is always different every week. Okay? The same question, which is different every week, is here's something, why don't you talk about it in class? Here's something else, why don't you talk about it in class? I very rarely talk about it in class. So I am going to talk about one of the things that you talked about in class, a little bit, not really to your satisfaction, I'm sure, but with a differing point of view, and we'll, answering not your question but mine, which is why don't I talk about this in class? So we will talk about the thing you asked me to talk about most recently, and I will give you all my reasons why I don't want to talk about it while I'm talking about it. Okay? What?
Do distance ladder or not?
I am not going to do the distance ladder until we get towards the end, right? Because, yeah, I'm not going to do the. I assume I won't. If I use up all the whatever stuff that comes up in my brain, then we'll get to the distance ladder. Prepare to the distance ladder. Are you disappointed today?
No.
No, I just wanted to know.
Add some addition to it.
Right. Well, listen, I owe my viewers, okay? You know, I have viewers, right? Viewers, right? Since last week I gained a viewer. Right. So now instead of having 21 subscribers, I now have 22 subscribers. Right. So they're picking up speed, and I promised them that I would do this distance ladder this time, but my real fear is that I'm going to run out of material. Okay,
Don't worry.
But you
I'll
know
get
everything.
plenty.
No, but the material you give me is stuff I don't want to talk about, and I'll tell you why. Okay, yeah. So let's talk about why. What is it that you wanted me to talk about that I don't want to talk about? Yes.
Just a short question, because I was 2 minutes late and you had Schrodinger's
Okay.
equation on. Why was Schrodinger up there when you walked in?
Why did I put Schrodinger's equation on the board?
Yeah.
Okay.
I missed you 2
It
minutes.
will no. I did not discuss.
Yesterday.
I did not. No, it wasn't. It's right here.
I was stunned. I was 2 minutes late and you guys.
And I got Schrodinger's equation on the board. Right.
Came,
I like to confuse you. I'm glad you
Solve
are.
that.
No, the whole point of having this on the board, okay, maybe I can just explain why I would put something like that on the board, given I'm not going to talk about it.
There we go.
Yeah, but I am going to talk about it in the sense of, look,
You've been talking for 15 minutes.
that's right.
But what are you talking about?
I come here to hear myself talk. I hope you come here to hear myself talk too.
That's true.
The reason I put this on the board is because of Elaine's question. Elaine has asked a question in one of the references that she sent me that I will not introduce at this moment, but in a few seconds. In a few seconds, I will say what Elaine's question is, but this is why I put it up. Elaine asked me a question that is truly wonderful in the sense of, if it was true, it would be magnificent. But the truth of what she's asking depends upon mathematics. It's all in the math. If the math is right, and if the math describes the universe, then the math becomes this beautiful object which we will all bow down to, pay homage to, say he's another Einstein, emblazon his equations on monuments throughout the world, and say what a genius he is. It's all about the equations. And then the words that are associated with the equations. But it's the beauty of the equations themselves that give you the feeling that, this is right, this is true. This is Schrodinger's equations. He wrote it 100 years ago. It has never, ever been shown to be inaccurate in any way. It is as good as gold. It's as good as Einstein's theory of general relativity. It stands on at the same height in the universe as Einstein's theory of general relativity. It's one of the most beautiful and succinct equations. I wanted to make it a little less succinct, okay, to make it a little bit more beautiful, or if not beautiful, at least confusing, so that you can appreciate there's some beauty in here, and even if you still don't know where the beauty is because you don't understand what's going on the screen, you at least know that when somebody, and what is your name?
Alexander.
Say again? Alexander, have you seen this equation before?
Oh yeah, a few times. I'll be honest, I don't really know what it means.
Okay, good. But you would agree that it may be one of the most beautiful equations ever written?
Pretty cool.
Yeah, pretty cool. So the truth in this equation also comes from the fact that it's beautiful, the fact that it has worked every time it's been used in an entire century, the fact that without his equations, your cell phones would not work at all, and without Einstein's equations, your cell phones wouldn't work at all. They're basically built upon two sets of incredibly esoteric equations that have been beaten down flat and made use of to create something that is in fact our civilization depends upon. This. Well, maybe what Elaine had to say, maybe there's something as beautiful out there, and maybe we just don't know what it is. Elaine keeps proposing these incredibly possible things that, if they were true, we'd have parades. At least the scientists would, you know. So I want to talk about her proposal, and then I want to talk about why I don't want to talk about her proposal.
I don't even know what.
Of course you don't, because you keep sending me proposals. I'm talking about the one that you focused on a few times, okay? And that one is this. So the thing that Elaine mailed me is a popularizing piece on the subject. I found the actual paper. So the actual paper is much more incomprehensible to read than what she read, but it's the thing that I like to read. And it's a unifying theory of dark energy and dark matter, negative masses and matter creation within the modified cosmic microwave background general relativity framework. The idea that we have these two things. What is this? A unified theory. We love unified theories. Us scientists, it is the best thing going. You know, if we could unify all of the laws of physics, we could go home, or at least take a weekend off. The idea that 95% of our universe is unknown to us. The 5% we know is the stuff that makes us all up. The 95% that we don't know, we have given the names of dark matter and dark energy, and they're not the same. One is matter, one is energy. They're not separate. They are separate. They were discovered separately. They explain different things. They seem to have no relation to one another. Dark matter is the thing that is sitting in the middle of every galaxy, so that the galaxies don't fly apart when they're whizzing around, you know. If there wasn't for the dark matter, the stars would go boom off into space, but the dark matter's hanging in there to keep those galaxies together. If it wasn't for them, galaxies would dissipate. So that's a thing that pulls together. Okay? And we don't know what it is, so we call it dark matter, but we think it's matter. And then there's dark energy. And dark energy is a thing that you don't need matter for. It just sits there in outer space, minding its own business, being repulsive, not attractive. And it pushes the galaxies away from one another, pushes them away. Okay, so push, pull, dark energy, dark matter, they don't have the same names. They don't have to do the same things. So this paper says unifying dark energy and dark matter negative masses, matter creation, he's got an idea. He has an idea that will put these two things together and make them all subject to the same equation, the same beautiful equation. Well, so why I went to the paper itself is because although you don't know equations from a hole in the wall, when you see one on the screen, you can go, oh, there's an equation. This guy must know something. Yes, he does. He knows that equation. It's the Einstein's field equations. And this is some other equations. It doesn't look like the previous ones. Clearly he's doing some math on them. Okay? And more math. And more stuff. There is an argument done with mathematics here in which the equations are saying, look, this is what I think, this is how you write it down, this is the way you describe reality in these beautiful equations that I have written down for you. There's some more beautiful equations. I'm clearly getting to the point where I'm going to be able to say, wouldn't it be wonderful if these equations described reality? And then I'm going just to the bottom of the paper. When he gets to the bottom of the paper, and I, for one, having read the paper, not carefully, but having read the paper, I have to admit, I am pretty impressed. This guy knows what he's talking about. He's a real scientist. He's not a crackpot. Okay? This is a scientist doing science. This is what scientists do. You've actually you've dropped in on the working of a scientific mind. And as such, the scientific mind needs to say one more thing, and there it is. A number of testable predictions have been made. Aha! That tells you two things. What he has proposed hasn't been tested, okay? Which means that he could have proposed that the universe was made up of silly putty, okay? And that explains everything. And until you do any kind of test to see whether he's right or wrong, he just has a hypothesis or theory. But he says there are testable predictions that have been made. For example, if the universe was made of silly putty, then when you took it and you made it into a ball and you threw it at the ground, it would bounce, okay? Because that's what silly putty does, okay? But if the universe doesn't behave like silly putty, then that wouldn't happen. Well, that isn't his prediction, that it's made of silly putty. He does, on the other hand, have actual predictions that his theory predicts that other theories don't. And therein lies the science. Because he suggests how to do it. And Elaine, if somebody picks up and does the job that he's done, and they get results that have never been gotten before, but his predictions predicted, then he won't be proven right necessarily, but will be well on the way to having an argument with all those people who are still alive who think that they know the answer. But he's younger, and he might outlast them all with his prediction that his theory works. And maybe in 30 years, if nobody gets to beat him down, maybe his theory will be correct 30 years from now, not today. And that's why I don't discuss it. Because not only are there other people out there who have theories, there are hundreds of them out there. I don't know, because I don't read the papers, how many other papers there are out there that are as good as this one. But and if I was really being a scientist, not some guy who comes here every week to just tell you some things I thought of last week, but if I was really a scientist, this would be my meat and potatoes. This is what I would absorb. I would love it. This would be everything I read. I wouldn't read any of the popularized articles at all. That's my job. when I was a student at Cornell, and there was this thing called the Astrophysical Journal. You have to realize this is 1965, 1972. That's the time I was there. Astrophysical Journal. It was a journal of articles about astronomy. It was this thick. It came out every 2 weeks, and I couldn't understand anything in it at all. So I would open it, and figuring that that was my job, to understand what was in it, I would try to find something that interested me, but it was so esoteric. I realized that for any one of these papers, I couldn't just start at the top. I had to go way down the hole and find out all the papers that had been written before, the history, all the people who were speaking about the conversation. I would have had to do an enormous amount of research to understand this one paper, because it was in my capability. I had the tools. I had taken 16 math courses since high school, so I could read this stuff. I could read it, I could write it, I could speak it. The only thing I couldn't do was understand it. So in order to understand it, I would have to spend a lot of time doing it. You all know, I left astronomy ultimately out of frustration for a lot of things, but also out of this frustration that I literally couldn't pick up the Astrophysical Journal and read it. And of course now it's people don't even see it physically. It used to occupy, shelves in the library. That this year's Astrophysical Journal, last year's Astrophysical Journal, and I was flabbergasted. They don't do that anymore. There are more people publishing than ever before, and they don't make physical copies anymore. It's all online, so it doesn't intimidate to the extent that it did before. Do you understand? Do you understand why I can't discuss everything if it is not yet at the level of proof, not theory?
Explain to me why that equation is so beautiful.
Why which equation?
The one you said, the Schrodinger,
Schrodinger's equation.
which was as good as Einstein's. What's the concept?
Right. Okay. Now I have to say, when I was in graduate school, this equation was something I studied. So I literally have passed exams and gotten A+ on that equation. But it's been 60 years, more or less, and so some of the actual facts escape me. But let's talk about what it's supposed to say. For one thing, I could not get why it was called the wave equation. The wave equation. To me, a wave looks like that. And want to see it again? Wave like that. What is true about that wave versus this wave? What's the difference between those two waves? There's two waves. You've just seen one, I drew it in the air. This is another wave. What's the difference between these two waves? Anybody? What?
Not moving.
It's not moving, right? This one is a wave in space. That one was a wave in time and space. Okay. Schrodinger's equation is a wave both in space and in time. I wrote down on the screen Schrodinger's equation in time, but Schrodinger's equation can also be in space. But what is the wave? What's waving? What's waving past you? What's going on? I graduated without knowing the answer to that, even though I had been told many, many times what it was. I'll tell you the answer to that, and then you can be confused. That is called a probability wave. A probability wave. A probability wave would be the fact that if you look and you plot where I've been standing in this room throughout this week in this course, there is a very large probability that I stand here. The probability that I stand here is less, and the probability that I stand over here is much less. So if you were drawing a probability wave of my position in this room, it would peak right in front of this computer. Probability of me being in front of the computer is quite high, statistically. Now pretend instead that I am a lowly electron. Could you ask them to close the door back there? Pretend I'm a lowly electron, and as such, I respond not to your general wishes and peer pressure, but I respond to the laws of quantum mechanics as written down by this law. And the laws of quantum mechanics say things like, you know, Laird, you're probably here, but you might be here, and you might be here, but you're probably here. But I don't know where you are, Laird, because it's impossible to know where you are. See, in the real world, you can always say, hey, Laird's right over there. But in the quantum world, it's all about probability, because reality doesn't set in the quantum world until you look. This is what's crazy about quantum mechanics. Quantum mechanics says reality doesn't look until you look. Reality doesn't exist until you look. If you're not looking, it might be, the electron might be here, you won't know it. It could be here, most probably here. That's what this is. It's a probability, it's an equation describing the probability that a particular electron or a set of electrons or a particular set of things that are all at the scale of atoms and protons and that level, where they are. And not only that, but then where they are as a function of time. The Laird used to be here, but now, because I measured him, but now I don't know where he is because the probability wave has spread out. Its probability waves spread out over time. We know this because it says it right there. And so while Laird, as an electron, is probably here, he could have spread out. So in fact, Laird is everywhere. Laird isn't in any place. Laird is has ceased to be a single object and is returned to being a probability of Laird. We can only know where Laird is by asking him, shaking his hand, and then we know. After that, we no longer know. So you can discover reality, but only by measuring it. In the absence of measuring it, reality doesn't exist. That's pretty crazy, summarizing all of quantum mechanics. And it's nevertheless true, which is even crazier. And the fact that you can have every scientist raised from 1920 to today believes what I just said. You believe what I just said, right? You've taken enough scientists to do this?
Me?
No, I'm asking, what is your name again?
Alexander?
Alexander.
Well, I'm still trying to find my way around like classical mechanics. So
You haven't hit this one yet.
Not yet.
Okay, so Alexander hasn't been hit on the head with quantum mechanics. Classical mechanics is easy. Things are where they're supposed to be. They don't misbehave. That's why it's beautiful. Did you have a question?
So what are you really saying about reality? It doesn't exist.
Oh yeah, I'm saying reality doesn't exist. Yeah. I'll write it on. I have it tattooed on your back. It doesn't exist. Okay. For microscopic objects, the macroscopic objects, we end up getting into conversations about truth. Right? Is there? How do we determine truth? And that is the second subject of what I want to talk about today, because I am not, if anything, an expert on truth. I cannot, every time I get involved in this sort of conversation with people, it doesn't always turn out well. And I'm sure the rest of you have the same problem. You say something that you, by accident, say it's true. And then someone else in your crowd comes at you with some sort of philosophical angle that they have been harboring for their entire life and they shoot you with it, right? That point of view on truth. And yet here I am about to talk about truth. What is it, Barbara?
So you're saying that it doesn't sound like science to me. It sounds like somewhere it's crossed the line. Because when you talk about reality in that way, it means that this chair is not here. It's not here unless you see it. But it's still here to me.
Okay.
So this whole thing about reality and science doesn't make sense.
Well, first of all, quantum mechanics is true. First thing about truth. Quantum mechanics is true in the sense of truth, only in the domain of small things, like electrons and protons. That is made up of something like 10 to the 26, 10 to the 30 protons and electrons. So it far exceeds the domain in which this equation has anything to say. Yet you can continuously discuss it. It will discuss it, but you can't solve it for the chair. You want to know whether what I talked about in quantum mechanics is still applicable in a domain in which quantum mechanics was never designed to speak of. It is not, if quantum mechanics was a human being and you asked it about that chair, it would say, I'm sorry, I have to go to the bathroom, I'd have to leave the room. There's no way they would answer that question. Quantum mechanics doesn't answer the question. The question is, at what point does quantum mechanics cease to want to weigh in on whether that's a chair or not? And I'm saying is, certainly, bottle cap is too big, okay? If I bite off a piece of the bottle cap, it's still too big. If I grind the bottle cap between my teeth and spit out the little pieces, those pieces are too big. The piece that quantum mechanics wants to address is smaller than anything you can imagine, and at that point, quantum mechanics weighs in and says, I have the truth. I'm going to go with Barbara again. Yes?
Just a question about that. That doesn't make sense because if the whole chair is in a different category and the minute part of the chair might not be there, if all the minute parts of the chair are not there, then the chair has ceased to exist.
Yeah, but the minute parts of the chair on the average end up being the chair. See, the distance that the smallest little piece could go is e, and the smallest the other little piece could go e, and they all together end up being right where they are. When you add them all up, you add up 10 to the 26 things that are almost here, and you get here. Exactly.
I don't think what you said is true.
Okay.
Because everything is built on quantum mechanics. This chair is a presentation of quantum mechanics.
Yes, it is. I'm not saying it's quantum mechanics is a presence, but if you and I start going down the rabbit hole of whether that chair is there, and whether it's a chair for that matter, we're going to be here all day and we're never going to get past that conversation. It's hard, and we can try, but it's really hard. What I'm trying to do is limit the unknown to saying we can talk about really small things, but we can't talk about the chair, okay? Because the chair is really hard, especially because if we brought a cat into this room and asked the cat what he thought about the chairs, well, the main problem would be the cat doesn't speak English, so we can't actually get the answer, and that's not just making shit up. That is true. Without language, that chair doesn't exist for that cat. You can't interview. He will sit on the chair, absolutely, but you cannot have a conversation with that cat about whether or not he's sitting on the chair. So it's your conversation with yourself about the cat sitting on the chair. So the cat doesn't get to weigh in. It's only us people with words that get to have a conversation about the cat sitting on the chair.
But Laird, everything is empty space. It's 99% of everything is empty space.
Yes.
And quantum mechanics is what makes this exist. Everything is empty. This is empty space.
Yeah, it is. It is, but when if you do the wave function calculation for two things instead of one. See, scientists do the wave function calculation for one electron. Okay, this is a very, very hard equation to solve. Extremely. It may look a little. I've made it look a little complicated. You have no idea how complicated it is. When they like to write the wave equation for an electron circling a proton, and they give it only to graduate students as homework. It takes them hours. Okay, one electron, one proton. Figure out where the electron is. Write the wave equation for the electron circling a proton. You want to solve it you want to write the wave equation for a chair? Good luck, because there's no computer in the world that could solve the wave equation for the chair.
You're right.
Right.
Your brain, your consciousness is creating this chair.
Okay, now we're getting crazy, because I agree with you. He said my consciousness is creating a chair, and I said I agree with him.
It's hard to sit on it then.
It's a bit, but I said I agree with you because basically, as far as things go, and I've been looking at this forever. As far as I can go, I go there. I actually go there. I actually say things like, my consciousness is creating the chair, and then I leave the room before anybody can tackle me as to what do you mean by that? Okay, would somebody like to challenge me, because he said it, and I'm going to back it up. Consciousness is creating the chair that Howard is sitting on. Could anybody argue against that for me? Just take a swing at it. Yeah.
So Ayn Rand came up with this philosophy called objectivism, and one of the assumptions is that there's an external reality from us.
It's an assumption. You said the word assumption, so you need to make an argument, not tell me what her assumptions are.
Okay. Well, I just wanted to...
If you can quote me by authority what other people said, that's not an argument in this class. Basically, you need to say why I'm wrong, why that doesn't make sense in some way.
I'll get back to you.
Okay, do. Yes.
First, we don't really know what consciousness is, so it doesn't help much.
It doesn't help much, right?
And also that object existing around, let's say, low-level animal where we think they don't have consciousness, and the objects are still there.
The objects are still, yeah. Well. Here's the thing.
And they were there before.
Here's a little bit of stuff, because when you go down this rabbit hole, you have to take a lot of crazy things down the hole with you. Okay, so if you believe in the insanity of this, consciousness creates the material world, and you also need to believe in universal consciousness. That when I see what
I don't.
You don't. Well, you'd have to, because in fact, then everybody's point of view would be manifested in different colored chairs in this room. Howard would be sitting in a pastel colored chair because that's what his reality creates, and other people who sit in pink and blue and purple chairs. They would all be different chairs depending on whose reality was creating things. But in the universal consciousness, if one person creates it in their mind, saying this is true, then it becomes true not only here, but for everybody else all the way across the universe. And Howard, you're going to love this, okay? You know that non-causality is your favorite thing. You like the idea that instantaneous action at a distance is the thing that keeps you up at night. You love it, right?
Non-locality.
Non-locality. So why not have consciousness be non-local, and have, when I look at that chair, everybody across the universe goes, yeah, it is a chair. I'm not there right now, but I'll take the non-local word for it. I know that if I get here, if it even takes me a million years, and if this room is still here, that chair will still be here, because Laird, at one point, consciously looked at it and said, yeah, it's a chair, and I made it so by my consciousness. That's how deep you have to go down the hole. So I don't want to go down that hole too much, although it happens to be my favorite hole. But there's no science in it. There's no science in it. That's in the realm of just, and I do believe it's not provable. I do believe that it's not science because it's not provable. It's not testable. And if any of what I said is testable, then it could become science. You wanted to say something.
Isn't there some attempt to conciliate the quantum world with the Einsteinian world, the small with the big, as like a unified field?
Yes.
It doesn't make sense to have two completely different
Yes.
theories. There is work going on to try and
Isn't there an attempt to unify the
reconcile. Yeah.
quantum mechanics and Einstein's theory of gravity? And I'm glad you asked that question, because basically that's the next important thing that I have to talk about. Yes, right. But I might have forgotten to say it. Because here's the thing.
And if you can do it in 5 minutes, right?
Yeah. I'm going to solve that in 5 minutes. Because, quantum mechanics, Einstein's theory of gravitation, I have no problem. 5 minutes, I'm done. I can do the whole thing. Okay. You need to know something called the double slit experiment. Okay? Have you heard of it?
Yes.
Okay. Who has not heard of the double slit experiment? 1, 2, 3. You have, but you just don't remember. Okay. I'm gonna tell you what the double slit experiment is. Okay. Without drawing it on the board, because that would mean me really explaining it to you. Instead, what I'm going to do is just walk around and wave my hands. There's an electron minding its own business on its way towards a target. On the way to the target, some experimenter has placed a thick sheet, aluminum sheet, with a teeny pinhole in it. And in that pinhole, and the electron is aimed for the pinhole. So the electron manages, some electrons don't hit the pinhole, but some electrons do hit the pinhole, go through the pinhole, and end up on the other side where there is an awaiting screen to record every electron hit. It's a counter, a Geiger counter, a photographic plate that records individual hits. And so you send a beam of electrons from an electron gun at it, okay? And now you get behind the screen, you get literally a pummeling of electrons that went through that little slit. Okay. If you put two holes very, very close to one another in the slit, you would expect to see two piles of electrons piling up behind the slit. A little bright spot here, another bright spot quite close to it. You would expect to see that. That would be classical mechanics. Things go through the hole, end up the other end, fine. That's not what you see. What you see is a wave, literally a wave, a probability wave. You see not a single peak and another peak. You see peak, 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 peak. You see a wave where these electrons look like they are ripples in a pond, and it looks like you've tapped two places in a pond, and the waves have gone out and interfered with each other as they hit the board, so that what you're seeing on the board behind is what's called an interference pattern. Are you with me so far? We have an interference pattern from the two electrons that have the two electron beams that have gone through. You go, well, that's okay. I'm not bothered by that, Laird, because clearly you sent too many electrons through the thing and they were interfering with each other as they went through the thing. So let's just slow this experiment down. Let's send in, instead of millions of electrons all at the same time, let's send them in one at a time. I know the experiment will take longer, but we got the time. Let's send the electrons through one at a time. It'll either go through one hole or the other hole. Of course, can't go through both. It's an electron. It's made of matter. It has to go through one hole or the other hole, of course. So we'll see which hole it piles up on, this hole or that hole. We'll see a pile of electrons here. We'll see a pile of electrons here. We're not going to see an interference pattern because we're sending in just one electron. And even though we're going to send in millions in this experiment, but one at a time, we're just going to see two piles like we did before. But we don't see two piles. We see an interference pattern. As if the electron went through both slits at the same time and interfered with itself. The electron is now behaving as a probability wave. And this is where I started losing it in college. Wait, wave, probability wave? What kind of wave? Isn't it a wave interfering with itself? No. It's a probability wave interfering with itself. And that's where I lost my marbles. A probability wave interfering with itself. An electron, two slits, you write the equations for it, and you end up using Schrodinger's equation with a wave that is the result of an electron having gone through both slits at the same time and interfered with itself. And you can't split an electron. The electron wasn't split. What did happen is the electron, because you don't know where it is, and because nobody was looking, it decided it didn't have to do what you expect it to do, because there is no reality, and it chose to go through both at the same time and behave as a wave instead of a particle. Yes?
I'm sure you've covered this already before I got here, but Schrodinger's cat is the same principle?
Yes. And we didn't cover it before, but no. But I'm not going to bring up Schrodinger's cat in this context. So that's pretty crazy. What you have is electron is now behaving as a wave, and it went through both particles, both holes. Okay. You asked me a question. What about Einstein's theory of gravity? Einstein's theory of gravity has nothing to say about quantum mechanics.
Well, I meant Einsteinian physics. in
You
general, right?
want to
Yeah,
talk
right,
about
big and
the
little.
gravity of things. That's what
Yeah.
Einstein talks about. Everything that has matter has gravity.
She wants to unify.
What happens?
Is there a unified field? Yeah.
No. You're going to miss the shocker if you mention words like unified theory. It's important, but we'll get there. What is important is when that electron went through one hole, and I told you it didn't go through one or the other. I said it decided when you weren't paying attention to become a probability wave and go through both. What about the gravity? Did the gravity become quantized as well and become a probability wave? Does gravity get quantized like electrons got quantized? Is there such a thing as quantized gravity? Well, there better be, but nobody has a theory for it. Nothing. Zero. We don't got a theory that would describe what an electron does gravitationally when it goes through. Clearly, when it's behaving like a wave and interfering with itself, is that electron when it's going through the thing, even though the electron's gravity is 10 to the minus 40th of what the electron is, but it's still got gravity, and it's still, gravity is going to interfere with itself, and the gravity that interferes with itself is going to create a gravitational wave that's going to interfere with itself. And so surely gravity has quantum properties. It's just that nobody on Earth has a viable theory that has been able to be tested to discuss quantum gravity. I'm just explaining to you why it's necessary, because you can't ignore it.
Yeah.
The electron went through two holes somehow at the same time. The electron did not split. It became a probability wave and went through it. Yes, no, not you, behind. Yes. Did you ask something? No, you didn't. Then you.
But the mass of an electron is so infinitesimal.
It doesn't make any difference. Infinitesimal is when you get to zero, let me know. Call me up. Otherwise, it still has mass and does everything else that it's supposed to do.
So you're hypothesizing that the smallness of the mass doesn't make a difference. It still has gravitational essence.
Right. It just happens to be immaterial and unmeasurable. but it can be measured by you adding them up. You get a lot of them. This has mass. There's a lot of electrons in
Well,
here.
that's a ton of them.
I know. It's made of electrons and protons. The electrons make up 1/2000th of the weight of this thing, so they're there. You can't take them away. I can count the number of electrons in here, and count the number of protons, and I can tell you the weight of each. And if you think it's different, then you've got a new idea of what the chemical elements and how they're made is. But basically, they're made of protons and electrons and neutrons. And that's it. And they have weight. They have mass. And you have to get a lot of them together in order to put them on a scale. But you can measure the mass of an electron. You can do it. It's easy to do it. What does truth mean to a scientist? What does truth mean to a scientist? That's the subject of today's lecture, by the way. I just didn't get to it for a while. But I think I've covered many of the points.
You started out with reality,
That's our reality.
but we didn't answer the question.
We didn't answer the question, but we can and we can't. That's a rabbit hole that I end up going down all the time. I should not do that. Okay, it's bad for my health and perhaps for these videos as well. What is true is his concluding sentence, which is no experiment we can ever prove that a scientific theory is true. This is nice, okay? Because basically this is words to Laird. Laird, please pay attention. No experiment can ever prove that a scientific theory is true. So why the hell do you keep speaking as if there's truth? Because I do, don't I? and I yell at you and I tell you this is true, and then you yell back at me. Well, isn't there something that we don't know? You do that all the time, Barbara. And so this paper is speaking to me about how I should speak to you. Nevertheless, I keep saying this is true. That is true. So we should get nuanced. And here's the nuances that he throws at it. It's simple. This example highlights. This example above highlights a few important ways of thinking scientifically that differ from how we think colloquially. Right. And basically, although I would like to speak as a scientist, what I tend to do is speak as a human being and then make the same mistakes, but you're expecting me to speak as a scientist. So these are mistakes that I made. There are no absolute truths in science. There are only approximate truths. Okay? I seem to ignore that point when I speak. Okay? Whether a statement, theory, or framework is true or not depends on quantitative factors and how closely you examine or measure the results. So I never give you nuances. I give you black and white. I don't. So I say, I'll tell you, the Earth is round. Somebody will raise their hand and say, no. Dr. Whitehill, the Earth is not round. It's an oblate spheroid. I stand corrected. Somebody else raises their hand and says, no. What about all the valleys and mountains? Right. So it depends on quantitative factors and how closely you examine or measure the results. There's no way that you can absolutely describe the shape of the Earth. Even if you took all the data points that we've measured from the sky, and even if we put all those data points together, and I pointed to the thing on the screen and I said, that is the shape of the Earth. Exactly, that is the Earth. Somebody, at this point probably somebody who's really trying to annoy me, would say, but that's not exactly the shape of the Earth. To what resolution has that been measured? And I would have to say, well, to maybe a few inches, and say, well, that's not exact. The Earth, and in fact, an interesting fact that I know is that if you ask somebody the length of a shoreline, it's It's great. What is the length of a shoreline? It's a trick question. They go, New York to L.A. to San Francisco, 500 miles. No, including all the coves. Oh, well, then and they come up with 600 miles. No, including all the little coves. Well, in that case, it's 700. There's absolutely no right answer to that question, because every grain of sand is another little cove, in and out, and in and out. And of course, the grain of sand has a certain amount of size and roughness to it. So the answer to the question of the distance of the shoreline between Los Angeles and San Francisco is a meaningless question unless you specify at what scale. And of course, we don't ever talk about that. So point number 2, it's how you measure the results. And point number 3, every scientific theory has a finite range of validity. Inside that range, the theory is indistinguishable from true. Outside of that range, the theory is no longer true. Okay, and we have for that some very good examples. So ones that you already know, which is certainly the theory of gravitation is a biggie, because Newton's theory of gravitation is not correct because there's a guy named Einstein who superseded it. Nevertheless, if you're building a multi-billion-dollar rocket to land on Mars, you do not use Einstein's equations, you use Newton's, because his is good enough, way good enough. There's almost no situation in which Einstein's theory of general relativity is needed for navigation purposes. There's a different thing when you talk about light travel time and telecommunications and all sorts of other things. That's a different story. But for navigation purposes alone, and then perhaps the universe, maybe all this business about dark matter and dark energy, maybe the reason that we're getting some funny results is because Einstein's theory of general relativity is only for things we can measure locally, but when you start going out to galaxies and the entire universe, maybe it doesn't work. Maybe his theory falls apart. Do you know how many people are employed full-time trying to kill Einstein's theory of general relativity with their equations? They're very successful.
What do they work for?
NASA. Everybody was funded by NASA, the government. Either that or you're a crackpot.
Or Xi Jinping.
Right. Or what?
Or Xi Jinping.
See, or she's.
Xi Jinping, Chinese premier.
Oh yeah. I mean, there are other people in other countries. I'm ignoring them, of course. That's a very real possibility, and people are trying to show that all the time. But there is no predictions that have been made, that have been tested, that show that they're right. So they continue to be like Elaine's question about her idea of, or this paper about negative energy, negative matter, matter that literally repels other matter. Not just because we don't have negative matter. There's no such thing as negative matter except in that paper. And in that paper says negative matter can explain dark energy and dark matter. All you need to do is have a little bit of froth of negative matter floating on top of positive matter. And since negative matter tends to repel positive matter, you have no problem. You can get your
What's antimatter?
Antimatter is unrelated. Antimatter is just the thing that is opposite of matter. It's subatomic and it's still matter. Still matter. Yes.
The theory that you talked about earlier, Schrodinger's, the split twin holes, tells us what you just said about truth, that you can't really know for sure truth if you know that theory that it can go through both holes by interfering with itself. That immediately tells you there's no such thing as truth.
No.
There's no such thing.
I disagree with you. I disagree with you because the truth is that we do not know whether it goes through both holes. We pretty much know it doesn't. The truth is that
Probability.
the truth is that it interferes with itself. That's true. And that we get a probability distribution of where the electron landed. That's also true, because we can measure it to as fine a level as we care to. If you want to say, you don't know, Laird, because you only measured 1 million electrons, I'll say, fine, I'll measure 1 billion. Tell me when it becomes true for you. So to any level of precision, the fact that an electron interferes with itself as it goes through a double slit is true. Which one it went through is not a question. Nobody ever, they have withdrawn the question. It is no longer a question. Nobody ever, they did. They actually tried. They said, aha, what we're going to do is we're going to sneak up on the electron. And we're going to measure which one it went through. And not only are we going to do that, but we're going to do it so as not to interfere with it. We're going to check only after it went through the hole. Okay? The electron will never suspect what we're doing. So if we measure after it went through the hole, we'll be able to see which one it went through. You think that's a good idea? It's a great idea. It's a very hard experiment to do, but they've done it. Best experiment ever, sneaking up an electron after it's gone through the hole to see which one it went through.
Because I've seen the path of an electron up at the huge electron accelerator.
Yeah.
And you can see it if it makes a cloud chamber. You can see where the electron goes.
Yeah, but we're talking about the double slit
Right.
and only the double slit. Okay, so we're talking about, and I'm not telling you how we measure it went through the slit, because I actually don't know. I do know that, just insert clever into the phrase, they cleverly measure the electron after it had been through the slit to determine which slit it had been through, thinking that they're going to still see the interference pattern, and they're going to know which slit it went through. But the electron is even more clever. It says, if you're going to play with me, I'm going to play with you, and I'm going to still, if you are able to determine which hole I went through, I'm going to simply pile up 2 piles of atoms behind each slit, and I'm going to stop interfering with myself. If you try to catch me, I will hide from you till the heavens come down from the sky. There's no way you can catch me at my game. And the electron has spoken to the scientists who have tried. And the scientists have tried, although they've not completely given up, pretty much they say, electron, you win. We can't figure out which hole you went through, and if we do, you're going to stop interfering with itself. So it's magic. It's literally magic. Quantum mechanics literally says you can't know certain things, and if you think you can get better at it, well, you're wrong. There is a law of nature, it's Schrodinger's law, which says you can't beat this thing. And they've been trying to beat it for 100 years, and you can't beat quantum mechanics. It's simply true. The electron becomes a wave function, goes through both holes. Okay. And by the way, there's something else you also know that also does something that's a wave and is a particle. Have you ever heard of a photon? Does a photon not strike you as being an object rather than a wave? A photon's a wave, and yet a photon is a point. So both photons are both waves and particles, and an electromagnetic wave is a wave and a particle, and an electron, which is a piece of mass, is both a wave and a particle. The difference is that an electron is a probability wave, and a photon is an electromagnetic wave. And that's why I also got confused, because I thought they should be the same. One is not probability, one is, but they're probably both. I don't understand this stuff. It's just, I mean, Einstein made his living from this. He got a Nobel Prize. He got a Nobel Prize for only one thing in his life, and it had nothing to do with quantum mechanics, with general relativity. He was the guy who proved that quanta existed, and then he spent the rest of his life denying it. He said, because everything that's quantum mechanics people said about quantum mechanics, he said, I can't believe that, in his words that have come down through the centuries that you now know as his phrase, and he did say something like it, God doesn't play dice with the universe. In other words, there's no way that statistical methods are the only way we can know things. Surely we should be able to know things independent of getting the average. We should, on the average, you throw a dice, it comes up a 7 50% of the time. Did you know that? You throw a pair of dice 50% of the time.
Because 6 and 1 and 3 and 4
Yeah, yes,
and
that's
4
it.
and 3
So the
and 1 and 6.
so the dice tells you the odds of throwing a 7 is 50%. Okay, but the odds of throwing a boxcars is 1 in 24, I guess. 1 in 36. 1 in 36.
Because it's missing step
Right.
6, yeah.
Right.
What if, just as a supposition, you're dealing with a higher dimensional reality with these things, and you're dealing with a platonic reality, something that we don't understand, that may be traveling faster than the speed of light. If there is such a thing that is traveling faster than the speed of light, which used to appear in Einstein's equations, and he factored out tachyons.
They're in there.
Huh?
They're in there.
So, but they may have something to do with what's happening.
Einstein's equations for general relativity and special relativity can be solved using tachyons. Tachyons are completely in there. Okay, but in order to explain tachyons, I would like you to give me, as a birthday present, the square root of -1.
Right.
Okay.
Well, we use the square root.
But give it to me. You gift me the square root of -1 as an entity, not as a concept, because the concept exists, it's a mathematical concept. But if tachyons are real, they also contain in their reality the square root of -1. And
The square root of -1 is used often in engineering.
there's no problem with it as long as we get the right answer. I use the square root of -1 all the time in my work. Well, I don't work anymore, but if I was working, it would be in there every second of everything I did all the time, including what was on this board before. There was the square root of -1 in there. There's a square root of -1 everywhere you look. Okay, because mathematics doesn't care. It's just when you get down to explaining what you see. Okay, that's when it cares. And if I need a tachyon to explain something, then I better be able to go out and find a tachyon, because otherwise it doesn't work as a theory. Anyway,
If it's at a higher dimensional reality, we can't perceive it.
it's possible, but again, I don't do that. Elaine.
So, will there ever be an understanding
Understanding of what?
of quantum?
We understand quantum theory. We understand quantum theory. What we don't understand is how to explain it to you. Okay. As a mathematician, I don't need to understand it because the equations speak to me. It's when you want me to explain the equations to you that things get out of hand.
Well,
Okay.
then you can never explain reality.
Well, see, the thing is, science is all about the math. What happens when the math leaps off the table and I have to explain it to you, that's where we start getting crazy. But the science is already there on the board, doesn't need explanation.
So you're saying that the math exists unto itself.
The math, there is a very definite way of thinking of things in which the universe is all about the math. So the question becomes, did we discover the math,
Did the math discover?
or did the math discover us?